Imagine a world where solar power never sleeps. No cloudy days, no nighttime interruptions, no seasonal dips, just constant, clean energy beamed directly from orbit. To many, this sounds like science fiction, but new research suggests it could become reality by 2050. In Europe, space-based solar power could cut battery needs by more than 70%, and combined with new ideas like solar trees that generate electricity without destroying forests, it could transform how we think about energy altogether. The concept of space solar power isn't new. It was first proposed in the 1960s by engineer Peter Glaser, who imagined giant solar farms in orbit beaming energy back to Earth. At the time, it was dismissed as fantasy, in the same category as moon colonies or nuclear-powered cars. But just as ground-based solar once seemed far-fetched, space-based solar is beginning to look plausible. Over the last decade, solar power on Earth has skyrocketed from around 1% of global electricity to over 7% today, becoming the cheapest source of energy in history. But the rise of renewables has created a new bottleneck: storage. The sun doesn't always shine, and the wind doesn't always blow. Grids require massive banks of batteries to balance supply and demand. That's where space comes in. Above Earth's atmosphere, in geostationary orbit 36,000 kilometers high, solar panels would bask in nearly uninterrupted sunlight. No clouds, no nights, no seasons. Two main system architectures have been proposed. The first, called the heliostat swarm, would use thousands of mirror-like reflectors orbiting in formation to concentrate sunlight onto a central collector. This design could provide near-constant output, with availability over 99.7% of the year. But it's extremely ambitious, requiring orbital robotics and precision control far beyond today's capabilities. The second design is simpler: a giant planar array, essentially an orbiting sandwich with solar panels on one side and microwave transmitters on the other. This could be built sooner, but it would only capture sunlight around 60% of the time. In a recent study, researchers modeled both of these designs within Europe's projected 2050 energy grid. The results were dramatic. The heliostat swarm design not only displaced huge amounts of wind and solar capacity, but also reduced the need for expensive batteries by more than 70%. The planar array had smaller benefits, but still contributed to grid stability. To make economic sense, though, costs would need to fall sharply. The heliostat system would need to be about 14 times more expensive per unit of power than terrestrial solar in 2050, while the planar array could break even at 9 times the cost. Today, these systems are still 1 to 2 orders of magnitude too expensive. But with reusable rockets cutting launch costs and orbital robotics advancing, those thresholds may not be impossible to reach. How exactly would this work in practice? The process starts with solar energy collection in orbit. Photovoltaic cells convert sunlight to electricity. This electricity is then converted into radio frequency energy, microwaves, using solid-state transmitters. The microwaves are beamed toward Earth in a carefully controlled, diffraction-limited beam. On the ground, vast receiving stations called rectennas, spanning several square kilometers, capture the microwave energy with dense arrays of dipole antennas and convert it back into electricity for the grid. There are natural questions about safety. People hear the word microwave and think of ovens. But the beam power densities in these designs are a fraction of that. The center of the beam might reach around 200 to 250 watts per square meter, roughly equivalent to midday sunlight, while the edges drop below 10 watts per square meter, in line with international safety standards. The highest intensity region would be fenced off, much like an industrial site, while the periphery could be used for agriculture or grazing. Fail-safe systems would be built in. If the satellite drifted out of alignment, the beam would automatically shut off. And since the frequency is in the industrial, scientific, and medical radio bands, typically 2.45 or 5.8 gigahertz, the spectrum can be managed through international coordination. Efficiency is another critical point. End to end, the chain from sunlight in space to electricity on the grid is estimated at 10 to 15%. That may sound low, but consider the advantages. Continuous sunlight, higher intensity than on Earth's surface, and no need for massive storage. For example, photovoltaic conversion might run at 35% efficiency, the DC to microwave conversion at 70%, transmission through space and atmosphere at over 90%, rectenna conversion back to DC at around 78%, and grid integration at about 90%. Multiplying those together gives roughly 14% overall. That is competitive when balanced against 24/7 uptime. Scale, however, is enormous. NASA's reference designs describe satellites spanning 10 to 20 square kilometers, with masses in the range of 6 to 10 million kilograms. The ground rectennas would be 4 to 6 kilometers in diameter, each delivering around 2 gigawatts of continuous power, comparable to a large nuclear plant. This means each installation could power a city the size of London. But it also means unprecedented logistics, orbital assembly, and international cooperation. Skeptics point out the obvious risks. Space debris could damage panels. Launching millions of kilograms of equipment could have environmental impacts of its own. Public opposition might rise against rectenna installations. And meanwhile, alternatives like continental-scale supergrids and long-duration storage technologies may mature, competing directly with SBSP. Even ESA acknowledges that many questions remain unanswered, from atmospheric interactions to maintenance costs. But supporters argue that given Europe's integrated grid and experience with multinational space projects, the region is uniquely positioned to lead. Japan, China, the United States, and India are already pursuing their own programs. If Europe hesitates, it risks falling behind in what could be a pivotal technology race. If space-based solar addresses the problem of intermittency, solar trees address the problem of land use. Flat solar farms require huge areas, often leading to deforestation or habitat loss. In South Korea, deforestation tied to solar farm construction quadrupled between 2016 and 2018. A recent study explored an alternative: vertical, tree-shaped solar installations designed to mimic the branching of real trees. Panels are mounted like leaves, angled for optimal sunlight, while allowing light to filter to the forest floor. In simulations, a single megawatt solar farm built as solar trees preserved 99% of the forest canopy, compared to just 2% survival under a conventional flat panel farm. About 63 solar trees, spaced 20 meters apart along trails and clearings, could match the output of a flat 1 megawatt installation, but without the need to clear vast tracts of forest. Beyond power, solar trees also provide shade for pedestrians and cars, reduce urban heat island effects, and can be equipped with charging ports or benches in cities. Challenges remain. Solar trees cost more to install than flat arrays, shading between branches reduces efficiency, and wind loads pose engineering problems. Manufacturers are only beginning to develop specialized designs. But in countries with high land costs, the smaller footprint could make them competitive. And as panel efficiency continues to improve, the drawbacks of shading will shrink. Taken together, these ideas sketch a future where clean energy doesn't always mean compromise. In cities, rooftops, and streets, solar panels quietly feed the grid. In forests and hillsides, solar trees produce electricity without clear-cutting ecosystems. Offshore wind turns steadily in the seas. Long-duration storage balances seasonal fluctuations. And in orbit, vast solar arrays beam down continuous power, providing a clean baseload source. No single technology will solve the climate challenge, but each has a role to play. Space solar is not ready to deploy tomorrow, and solar trees are still in experimental stages. But both remind us that innovation can widen the menu of solutions. If we invest in research and test these ideas today, by 2050 they could be integral parts of a global net-zero energy system. The future of power may not just be on rooftops or in deserts. It might be in the forests we preserve and in the satellites that hang above the sky itself.